Welcome to today's deep dive. We are jumping straight into tutorial 4, which covers Ethernet switching.
Yes, and this maps directly to your IE 1030 Data Communication Network's lecture notes. So grab those if you have them.
Exactly. And look, if you are sitting there feeling like an absolute beginner, maybe feeling a little lost, take a deep breath.
Yeah.
We are building this from the ground up today.
Yeah, no student is getting left behind. We have a very strict mission. We're going to break down every single question from this tutorial one by one.
Right. And we're using a very specific 5-step blueprint for every single problem.
Right. Step 1, we read the exact question word for word. Step 2, we trace it right back to your lecture slides.
Step 3 is the exam strategy, right? Like the actual tactical logic you need to score full marks.
Exactly. Then step 4, we give you the final exact answer to write down. And finally, step 5, we unpack the high-level, PhD-level theory using real-world analogies.
I love that. Making the abstract actually makes sense.
Right.
So let's just dive right into question 1.
Let's do it.
Okay, step 1, reading the question word for word. For which purpose is the special MAC address FF, 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 FF used, and in which field of the Ethernet frame can it be used?
Okay, step 2, tracing this to your notes. You will find this directly in your link layer lecture slides, specifically the section covering Ethernet frame structure and hardware addresses.
Right, so for step 3, the exam strategy, when you see that string of Fs, you need to recognize that it's the all ones hex code.
Yeah, 48 ones in binary.
Exactly. You associate that with its function, forcing everyone to listen and then pinpoint where it physically sits in the header.
Right, which brings us to step 4, the exact answer you write on your exam script.
Lay it on us.
For purpose, you write, it is the broadcast address used to send a frame to all hosts on the network.
And for the field?
For field, you write, it is placed in the destination MAC address field. That's your full credit answer.
Boom. Okay. Step 5, the PhD level deep dive. Think of using this specific MIC address like grabbing a megaphone in a really crowded room.
I like that.
Right. Instead of handing a private note to one specific person, you're just blasting the message to everyone.
Yeah, and it's totally necessary for basic network communication. Like when a device first wakes up, it's completely blind. It has to yell with that megaphone just to find the router or other devices.
It's the only way to solve that cold start problem. Okay, moving on to question 2. Step 1, reading it word for word.
Go for it.
Explain what is meant by the following terms. Collision domain.
Awesome. Step 2, tracing it. You'll find this in the CS-MAN-C section of your lecture slides, and also where the notes compare topologies like bus and hub setups versus star and switch setups.
Makes sense. So step 3, exam strategy. The trick here is breaking this into 2 totally distinct concepts, right?
Exactly. One is the physical event, the actual crash, and the other is the geographical or logical boundary where that crash actually matters.
Right, so step 4, the final exam answer. What's the definition for a collision?
Write this down. Collision occurs when more than one host transmits data on a shared medium at the exact same time, causing the signals to garble.
And for collision domain?
Collision domain, a single network segment where collisions can occur. For example, all links on a hub form one domain, whereas each port on a switch is its own separate collision domain.
Okay, step 5, let's deep dive this with an analogy. Picture a really narrow one-lane bridge over a river.
Oh, right, the one-lane bridge.
Yeah, a collision is, well, what happens when 2 cars enter from opposite sides at the exact same time and just smash into each other?
And the entire bridge itself of the physical space is the collision domain.
Exactly. So to stop those crashes, networks use a rule called CSM-50. It's basically a super polite, listen before you speak traffic rule for the bridge.
Right, if you hear traffic, you wait. It prevents the signal from turning into just pure electrical garbage on the wire.
Perfect. Okay, question 3. This one is a bit of a beast. It has subparts.
We can handle it.
Step 1, word for word. Consider 6 hosts, A through F, connected to a networking device. Can the following pairs of frames be sent simultaneously without collision? Answer for a half-duplex switch, a full-duplex switch, and a hub.
Right, and there are 3 scenarios to evaluate. Step 2, tracing. This links directly back to your lecture concepts, comparing CS-MIDI on half-duplex versus the active capabilities of a switch on full-duplex.
Step 3, exam strategy. Let's make a tactical grid in our heads. Rule 1, a hub is just a dumb repeater. It shares everything, so any simultaneous sending automatically fails.
Yes. Rule 2, half-duplex means a link is just a one-way street at any given time.
And Rule 3, Full duplex is a two-way street, so simultaneous traffic is fine, but, and this is the trap, you still cannot jam two different frames out of the exact same destination port at the exact same time.
Exactly. A single port only has one exit lane. So, step 4, let's dictate the exact matrix for the exam.
Okay, scenario A. Frame from A to F and a frame from F to C.
Switch half duplex.
Yeah.
And no. Switch full duplex. Yes. Hub and no.
Got it. Scenario B. Frame from C to F and a frame from B to E.
Switch half duplex. Yes.
Yeah.
Switch full duplex. Yes. Hub no.
And finally, scenario C. Frame from F to C and a frame from A to C.
Switch half duplex. And no. Switch full duplex. And no, because they both go to C. And hub and no.
Okay, step 5, the deep dive. The easiest way to picture this is walkie-talkies versus a modern phone call.
Right. Half duplex is the walkie-talkie. You have to push the button, talk, and say over before the other person can reply.
Exactly. You can't talk and listen at the same time. But full duplex is a modern phone call. We can both yell at each other simultaneously and still hear it all.
And tying it to the devices, a hub is basically a noisy party line where everyone is just shouting over each other.
Yeah, complete chaos. While a switch is like a really efficient vintage switchboard operator.
Exactly. Managing totally private, isolated conversations between callers.
Beautiful. Okay, question 4. Step 1, word for word. Explain how a switch will forward each of the following frames. A, frame with destination MAC and switch table. B, dest MSC not in table. C, broadcast frame.
Step 2, tracing. This is pulled straight from the flowchart in your lecture titled Address Learning and Forwarding.
Okay, step 3, the strategy. This is just a basic logic gate, right?
Yeah, the switch makes an instantaneous routing decision purely based on its internal table. It just asks, do I know this address?
The step 4, the exact answers for the exam. For part A, destination MSC is in the table.
You right. Selectively forward the frame only out of the specific port listed in the table.
Part B, destination MSC is not in the table.
You right. Flood the frame on all ports except the incoming port.
And part C, a broadcast frame.
Also right. Flood the frame on all ports except the incoming port.
Okay, step 5, the PhD analogy. Let's talk about a corporate mail sorting room.
Oh, I like this one.
Yeah, so if the mailroom clerk looks at an envelope and knows exactly which office you're in, meaning there's a table match, they deliver it directly to you. That's selective forwarding.
Right, but if you're a new hire and they don't know where you sit, they don't just throw the letter away.
Exactly. They get on the building's intercom and page every single room in the building except the sender's room, asking where you are. That's flooding.
And it's incredibly elegant. It's a plug-and-play, self-learning design. Nobody has to program the mail room.
Which perfectly sets us up for question 5, the big one.
This is a massive question, yeah.
Step 1, I'm going to read this word for word. Consider the network below with 4 switches, S1, S2, S3, and S4. Assume that all switch tables are initially empty. The time to live, or TTL, is 300 seconds, decrementing by 1 each second. Show the switch tables after the following frames have been sent. At T0, host A sends a frame to host G.
Right.
At T10, host G sends a frame to host A, and at T20, host E sends a broadcast frame.
Okay, step 2, trace this. This is the self-learning and forwarding example slides. It shows exactly how AMC tables are built dynamically and how they age out over time.
Step 3, exam strategy. For a problem this big, you need a systematic timeline approach, right?
Exactly. You trace the physical path of the frame, you record the incoming port and the source MAC in each switch's table.
And you have to calculate the TTO by subtracting the elapsed seconds.
Right, and then decide whether to flood or forward based on the destination. So, step 4, let's dictate the exact outputs for the exam script. This is dense, so keep up.
Ready. First up, at T0, Vero A sends to G.
The frame is flooded by S1, S4, S3, and S2 because G is currently unknown.
Okay, and what did the tables learn?
They all learn A's MSE address. S1 logs it on port 1, TTL 300. S4 logs it on port 1, TTL 300. S3 logs it on port 4, TTL 300. And S2 logs it on port 4, TTL 300.
Awesome. Now at T10, G replies to A.
The frame is selectively forwarded along the path from G to S3 to S4 to S1 and finally to A.
Because A is already in their tables in the first step.
Exactly. It does not go to S2. Now for the tables, they learn G's MAC with a new TTL of 300, S3 on port 1, S4 on port 3, S1 on port 4.
And what about A's previous TTLs?
10 seconds have passed, so A's TTL in those tables drops to 290.
Perfect. Final event at T20, E sends a broadcast frame.
Since it's a broadcast, the frame is flooded everywhere.
Right.
The tables now learn E's MAC, with a fresh TTL of 300 at S2 port 2, S4 port 2, S1 port 4, and S3 port 4.
And the older entries drop again, right?
Yes. A's TTL drops another 10 seconds to 280, and G's TTL drops by 10 seconds down to 290.
Phew. That is the complete answer matrix.
It is.
So, step 5, the deep dive. How do we visualize this self-learning? Think of the fairy tale of Hansel and Gretel leaving breadcrumbs in the forest.
Right. The source MSC addresses are the breadcrumbs.
Exactly. When a frame enters a switch, it leaves a little breadcrumb saying, I came from this specific port.
And the TTL, that 300-second timer, is basically how quickly the birds eat the breadcrumbs.
Wow. Yeah, if you wait too long, the path disappears.
Precisely. Flooding is what creates the map initially, but selective forwarding is just following those breadcrumbs back home before they vanish.
That brings us to the end of the tutorial. If you followed along, congratulations, you just made it through a really complex, university-level networking concept.
You really did. This logic is the absolute foundation of how the entire internet infrastructure operates locally.
So to wrap up, we like to leave you with a provocative thought to explore on your own.
Right. So consider this. We just learned that a switch automatically learns and entirely trusts every single source MEC address it sees to build its table.
It's totally blind trust.
Exactly. So what happens if a malicious actor intentionally plugs in a laptop and sends hundreds of thousands of frames every single second, but with fake source MA addresses?
Oh, wow. So they're just dropping millions of fake breadcrumbs everywhere.
Yes. Can those fake breadcrumbs be used to completely overwhelm the switch's memory? What happens to the network when the table overflows?
That is a terrifying thought to leave off on. Explore that on your own. Keep questioning the infrastructure around you, and we will catch you on the next deep dive.